Data Storage in Outer Space, Overcoming the Obstacles, by our very own Dr. Tom Coughlin of Coughlin and Associates. Tom set up his QR code so that you can jump to Tom Coughlin on LinkedIn just by scanning that. It'll also come up at the end on the final contact slide, but I thought it would be good right up front. So let me tell you a little bit about Tom Coughlin, if you don't already know it. You know, Tom's a pretty famous guy. He was president of the whole IEEE in 2024, over 500,000 members. And I voted for him 3 different times, I think, and he won. So, yeah, different elections. Right. I don't mean fake voting or, you know, oh yeah, I didn't even think about that. This is California after all. So this could be, I'm throwing in extra votes for Tom. No, 1 vote, 1 election, never voted more than once. So, but Tom was president of IEEE in 2024. Tom is actually the guy who got me involved with IEEE. I met you way back when you were running at that time it was called GOLD, Graduates of the Last Decade. That's now YP, Young Professionals. I went to one of those and there was Tom Coughlin running the whole thing. And, you know, he was pretty smooth. Even then, this must have been easily 25 years ago, maybe more. So Tom is definitely a person who brings in people, gets them active, gets volunteer work out of them, and he's just a great man. He's a consultant in the storage industry. He writes columns for Forbes every month to 2 months, something like that, kind of free. 6 a month. Okay, so you can find Tom on Forbes when you look there, and some of his storage work. Tom is also a honcho for the FMS conference that's upcoming. Tom Coughlin, Brian Berg are 2 key people with that conference. And so he's an all-around great asset. He's a great asset to our group. He's been chair in the past. He's been a director for a number of years. So I don't know what else to say, Tom. I mean, is that it? Yeah. All right. So everybody welcome Tom Coughlin. Let me swap presentations here. I need to go to yours now, and then share it again. Yeah, that's right. Right, I got to go there, but I want to share, and now share again. And then we probably better ask out there that it's really.
Can you hear me okay?
Yeah. Here's your mic right here. Yeah, that's the mic right there. All right, and then share, and then let's go here. And then let's be sure that everybody gets it. Other raised hands. All right, just a second.
I think those are fossils.
All right, there are 2 of you. Interesting. Okay. Oh, 2 of me probably. All right, and let me change this because it's going to be Tom Coughlin speaking. Rename.
So, how many of you are science fiction fans? Yeah, me too. I thought by with the landings on the moon back.
Tom, make sure you're close enough to the mic though. Yeah, you got to be back here a little bit to be in front of this.
So I thought by the time I was this age, I'd be a crusty old asteroid miner. And it was kind of disappointing that we didn't keep on going, for years. So it's really may finally be happening that human beings and our equipment are going to be actually making an impact, not just on the Earth, but also elsewhere as well. And I think it'll open up huge opportunities.
So let me just be sure it's not advancing. Just
so this is a SpaceX image.
Yeah. Go ahead and talk about that.
Yeah, this is the I think it's a Google. An NVIDIA H100. Oh well,
I'm
on that
back.
thing. It was make a data center in outer space. You can't hear me? Okay, can you hear me now? That's good.
It's
okay.
A little louder. Yeah, because in here they don't get a microphone.
They don't get a microphone. Okay.
Microphone is only for Zoom then.
Are we ready?
I think so. Let me be sure. It's a little flaky with advancing, but let's see.
I
can definitely do it here. I can definitely do it with arrows, but I don't want you to have to do that.
Well, I
But
can do that.
Should we do that?
Yeah.
Just arrow key.
Yeah.
And if you want for in the room, this doesn't help on Zoom, but if you want to put it out on for the room, the upper is the green arrow.
Thank you.
But
Thank you, Ken. Okay,
Tom Coughlin.
So thanks for the opportunity to be able to talk here today. Can you hear me okay now? Is that good? All right, I'll try to keep that up. So anyway, so I've always thought it would be cool. We should be out there, and I think it's finally coming to a head. So I'm going to talk today a bit about my observations and thinking on this, and that some challenges about outer space, but also opportunities. The idea of data centers in space, both communication and computing, and about an area that is what I work in, which is memory and storage, and to talk about that technology in particular for its applications, both in low Earth orbit, but elsewhere in outer space as well. Finally, we'll talk about the future at Astra to the stars, and then I want to talk a little bit about some things that are going on in the IEEE that are related to space, which might be a summary and a bunch of references. So the challenges and opportunities. This is the Artemis 2 rocket that took off a month ago or so. I guess it's almost a month and a half now there. And one of the big things that's changed an awful lot is going from the space program back in the 1960s, early 70s, is the cost of transportation and bringing stuff into outer space, particularly inanimate things in outer space like machines, is gone down enormously. It was roughly about $22,000 per kilogram during the Apollo program, and again in the late 60s and the early 1970s. And it's about $2,720 per kilogram with the SpaceX Falcon 9. But if you look at this chart over on the right-hand side, and most of this is looking at the SpaceX devices there, they're talking about going down into the hundreds of dollars, even $100. In fact, someone is saying even less, per kilogram. And that changes the equation enormously and opens up opportunities which wouldn't be there otherwise. More people can think about getting in things into space. You can think about doing more stuff in space. Now, if you get people in the equation, then you have to have the life support and everything else. That changes the cost based on that. But even that will benefit from the lower transportation costs. So just a little bit of background on related to what's going on here. And furthermore, the big thing that when you're leaving the Earth, the most energy you're spending is just doing that. It's getting out of the gravity well. So most of the energy of a modern spacecraft is spent getting into orbit or beyond orbit. For the Artemis 2, they had over 700,000 gallons of propellant were used to escape the Earth. But once you're out in space, it's movement relied upon efficient small maneuvers and also gravitational assists. They talk about things like if you go around the moon, for instance, you can do it in such a way that you actually gain some acceleration. You get some energy essentially by doing that. So that's a gravitational assist. And so once you're in outer space, and that's the important thing I think to realize is when you get out there and when you start having things that happen there, this is sort of self-perpetuating in a way in that it takes very little energy to get around. And let me talk to you a little bit about some of the propulsion systems they're talking about for doing that. So we can use lower energy propulsion systems to getting around in space. Things called ion thrusters, for example, like that's shown on the right-hand side here, are high-efficiency electric engines. They use electromagnetic fields to accelerate ions, that is charged atoms, and produce low-thrust, high-velocity propulsion. And they can do this for a fairly long period of time because they consume 90% less propellant than chemical rockets. So they're ideal for long-duration space missions, for example. Solar sails are another technology. We're actually using the light from the sun to basically reflective sail, they call it, that actually experiences propulsion by doing that. It's recording in progress. And also people are talking about going a step beyond that, where they're using lasers, not only just light coming from the sun, but they actually use lasers directed at a solar sail, if you will, or a device like that, in order to be able to provide more thrust and for longer periods of time. Than they might even talk about that as a possible way of moving things around for long distance space travel. So in addition, vehicles meant only for use in space can be built very differently from those that are designed to handle the high shock, high vibration environments of launching. So once you're in outer space and you build stuff that's just moving around in outer space, they can be constructed a lot less strongly. They could use less materials, for example. They still have to be able to do what they're supposed to do, but they don't have to. There can be simpler and devices that could deal with that environment. There's other challenges, but you can basically construction is less of a burden there. Also, communication is an important factor. The Artemis 2 Hello World was downlinked to Earth using lasers to transmit data, and they said it was up to 100 times faster than with traditional radio. Lasers there's this laser comm is used in satellite networks like Starlink, for example. So it could be used for, if you have little modules out in outer space, they can communicate directly with each other using lasers. There's a European company called Astrolite that's developed a 10 by 10 centimeter laser, lower cost system that can be integrated into satellites, for example, as well. So communication is another important factor. There are challenges too, and one of them is all the stuff we've already is about 54,000 space objects, and their total mass is about 16,200 tons. The estimated number of fragmentation events that have occurred is about 660, and many of these objects burn up entering Earth's atmosphere, but many don't, and they hit each other, and they make even more fragments. And people have talked about this being something that could be propagated and cause a lot of issues. With current launch schedules, people talking about putting 1 million objects into space, or tens of thousands, or that space is going to get kind of crowded. So I think we're going to need some kind of garbage collection capability, to be able to get this stuff. And I think it's kind of a waste to burn it up, let it go in the Earth's atmosphere. Besides, put stuff in the Earth's atmosphere. I think it'd be better if you actually pick that stuff up and put it someplace where you can use it later on, because it costs a lot to bring stuff up there. Let's put it in one of the Lagrangian points and then use that as raw materials later on.
Kind of space recycling.
Exactly. Yeah. I think that would make sense. So, but that's on the communication side. So lasers are one way that could be used, of course, regular radios, but there also is the whole protocols of how you can communicate in outer space. So Vint Cerf, who's known as one of the pioneers of TCP/IP, and developing the basic technologies behind the internet, pioneered the concept of an interplanetary internet, which connected different types of space assets to each other and connected those assets with the Earth. So this interplanetary internet is envisioned as a store and forward network of internets that is often disconnected, has a wireless backbone fraught with error-prone links and delays ranging from tens of minutes to even hours. And even when there is a connection, it can be, there could be issues in that. So you have to wait until things are lined up. So if you're on Mars and you want to communicate with someplace on Earth, you have to wait until things can line up to do that. And so that's why they're talking about actually storage would be an important part of the communication. You're going to keep a piece of data to transfer when you have the opportunity. Okay. So participating communication nodes in this interplanetary communication will keep changing over time due to the constant motion of these bodies. And the routes of the interplanetary communication need to be planned and scheduled rather than being opportunistic, as is common on the internet today. So it's a different kind of communication you're going to be needing. So because of the delays in relaying messages over the vast distances of outer space, local systems must have significant autonomy to be able to make real-time decisions. This processing and the store and forward interplanetary networking will drive the need, I believe, for data centers in space and close to the equipment that they manage. In other words, we're going to put data centers in space because we need it to do stuff in space. So that's the basic premise of what I'm talking about. So let's look at data centers in space. So why do we need this? I think physical AI, that is autonomous or semi-autonomous robots in particular, in space can stay in space, creating infrastructure and harvesting materials for the further development of outer space. And they could do that, as you can see, for lower and lower costs of bringing that stuff up there. So much of future space development, I think, will include robots and AI because it's cheaper, because you don't have to build the life support. Doesn't mean people aren't going to go there, but you're going to go there. People are going to go there where they're needed to be. And it's cheaper and less risk to humans if we let machines do a lot of the work. And so I think that, again, that physical AI is going to be a big driver for this. And that will require local data processing, communication infrastructure that reduces the latency and enable more real-time control versus waiting minutes or even hours to get information back from the Earth, for example. So I think we're going to need data centers and space communication to enable the development and the humanization of outer space. So what does this look like? So cheaper transportation of space makes it easier and less of a burden to do more things in space. So this could, for instance, be involved in collecting and using solar energy. There's a lot of that out there. Setting up new and more powerful telescopes, including very sensitive gravity wave observatories in space, and making factories for the production of goods, space infrastructure, and new space vehicles. Recently, word leaked out about SpaceX's Starfall program for delivering goods from orbital factories. It's actually a way of dropping it to the Earth with these Starfall devices. Yes. So these scientific transportation industrial systems will likely be highly automated, and it's an example of that physical AI. And we'll need local as well as distributed data centers and space-based communication networks to connect them in the Earth. In addition, energy constraints and issues such as water cooling are one of the biggest challenges in building Earth-based data centers for large AI deployment. In outer space, there's abundant energy available from the sun for doing all kinds of things, including AI and various types of high-performance computing. Space-based data centers will be able to communicate directly, although with some latency and potential delays, to multiple Earth locations, creating new accessibility for extraterrestrial cloud resources. So it's another thing they can all offer capabilities to the Earth. I think that's part of it, but I think the big thing is going to be just building the capability for doing things in space. So here's a bit of history. I've been watching this for a little while and writing some of this in some of my blogs and things. Back in 2016, a startup named Cloud Constellation wanted to build an array of equatorial low Earth orbiting data center satellites in order to produce a space-based infrastructure for cloud service providers so they could better serve corporate and government clients. So the digital storage would be used in these orbiting data centers was to be solid-state drives, so NAND-based solid-state drives. In December of 2022, Lone Star Data Holdings announced that we wanted to build a data center on the moon for backing up the Earth's data and also supporting lunar edge processing needs. 2025, last year, was a busy year for outer space data centers and the digital storage technology demonstrations in those data centers. In January of that year, Flexential, a major data center provider, and Lone Star Data Holdings said that they would collaborate to support the then upcoming launch of Freedom, its second project to create a data center on the moon with intuitive machines, Nova-C lunar lander, which was to be launched on a SpaceX Falcon 9 rocket. So about the same time, another lunar lander embarked on a journey to the moon carrying NFT tokens and a significant piece of historical data encoded on synthetic DNA from startup Iridia. This was encapsulated within a monument symbolizing humanity's achievements and carried in LifeShip Luna's payload on the Dragonfly Aerospace Blue Ghost lander, a picture of which is shown here. So the one that Lone Star sent actually tipped over when it landed on the moon. It's kind of top heavy. This one, as you can see, is kind of a squat little guy. Yeah. And so he had better odds when he landed on the moon. So let's see. Oops.
Hard to pick up.
That's okay. Thanks. Thanks. Let's see. I'm trying to go to the next one here. There it is. Okay. So some more developments. In September 2025, Axiom Space and Space Built Incorporated announced a collaboration to bring optically interconnected orbital data center infrastructure to the International Space Station in 2027. So this infrastructure will include an optical communications terminal by Skyloom, storage and other hardware from Phison Electronics, and microchip technology. So the system is intended to allow satellites, other spacecraft in low Earth orbit, and astronauts and researchers to store and process data and run AI workloads in cloud computing applications. This builds upon results from the Axion Data Center Unit 1 delivered to the space station in August of 2025. In November 2025, NVIDIA-backed startup StarCloud, which some of you have heard of, launched an NVIDIA H100 GPU into orbit on its StarCloud 1 satellite. In fact, I think that was the picture at the very beginning of my presentation. While in space, the StarCloud satellite was able to train and run a large language model using NanoGPT running on the complete works of Shakespeare. So the model was then able to answer queries in Shakespearean English. It was also been running and querying responses using Gamma, an open language model from Google based on Gemini. The next satellite launch will include several NVIDIA H100 chips and integrate NVIDIA's Blackwell platform. Is scheduled to launch in October of this year, and will run a cloud platform from cloud infrastructure startup. Well, I don't have it there, but in October of last year, Google unveiled their initiative called Not to Be Outdone, a Starcatcher that aims to put solar-powered satellites into space with Google Tensor Processing Units. Another company, Aetherlux, announced a target to deploy an orbital data center satellite in the first quarter of next year. Cowboy Space, out of San Carlos, California, I like that name, wants to begin launching 20,000 satellite orbital data center constellation by 2028. So in general, it seems like everybody and their brother is jumping on this, and perhaps the stars are aligned on creating an international data sphere, an extraterrestrial data sphere, excuse me. So here's some interesting articles on it here. Remember I talked about that Lone Star Freedom? So that black thing, that's the data center. Not much to look at right there, but it was carried in February 2025. This is from an IEEE Spectrum article, February last year. Intuitive Machines mission lunar lander. Among other things, the lander contained this mini data center. It weighed about 1 kilogram and contained 8 terabytes of SSD storage. So it's like a little mini data center, just to show what you could do with that. It was a proof of concept from this Lone Star data holdings. So as I mentioned before, this whole rocket was pretty tall, so it's kind of top heavy. And when it did land, it landed at an angle, it fell over, and they never really got anything much out of it. This is from this year, February 2026. This is actually related to the costs of actually building a data center. So this is again an article on IEEE Spectrum, February this year. It's a version of a data farm satellite, and then they're going to talk about how much this costs versus doing this on the Earth. So the basic configuration here is 1,024 square meters of photovoltaic panels that are generating 240 kilowatts. Cooling could be done by circulating a fluid among the processors and into channels of radiator panels. And by the way, that's one of the big challenges of doing things in outer space. You don't have convection. So that means surface area. And so, that's what it was doing. The satellite would have 2 racks of GPUs, each with 72 GPUs in the rack. And then to create a gigawatt of processing power required 4,300 of such satellites. So these are not tiny things, but they're not really huge things either. So
Tom, this is proposed. That one is.
No, this is an analysis that was done, and then the next slide is actually from the same article. It's talking about what the cost of doing this on Earth would be versus doing it in outer space. So, so some of the richest, most powerful people in technology are backing these data centers in space. Elon Musk, Jeff Bezos, Jensen Huang, Sam Altman, Google CEO Sundar Pichai. I think I was just saying earlier, I don't think Microsoft jumped in there yet, but you know. Yeah, they're behind. Yeah. Aerospace engineer Andrew McCallop estimates that the cost of an orbital data center described in this last slide would be about 3 times that of a comparable terrestrial one using modern radiation-resistant technology, which, when you think about it, it's more expensive, but it's not that much more expensive.
Class V, class K, 100x.
So, you know.
100x the traditional commercial off the shelf.
So what is?
Just looked at that. I'm a little astonished with 3x.
He said 3x, yeah. But again, you know.
Look at class V and class K devices, and they're like 100x.
Are you talking about the radiation resistant devices? Is that what you mean?
No, semiconductors.
The semiconductors, yeah. Yeah. Anyway, but that was his analysis, say to be about 3 times more. And part of it is the cost is going down to bring things up there, even if they are more expensive, and that's probably some part of this. So, so let's talk about memory and storage in space, a bit about the data center side of these things. So memory and storage are critical for data collection, retention, and processing. They'll be such in space as they are on the Earth. And outer space exposes electronic devices to challenges that are not common on the Earth, like a high radiation environment, where you have ionizing, non-ionizing radiation and extreme events during solar storms. It's particularly bad for charged-based devices, where you can have, they can cause soft or even hard permanent errors in these devices. So also, smaller lithographic feature sizes may actually be more sensitive to radiation for these devices than larger ones would be. And then there's extremes of heat and cold, and the lack of convection to remove heat in space unless you actually bring your air with you, right? So, so for applications launched from and landing on Earth, shock and vibration from launch and landing, of course, are issues. And for some applications, there may be power constraints or related heat dissipation constraints you could do. And temperature regulation in particular may favor computing and processing in smaller things that have a higher surface area, or creating a high surface area because you need that to radiate the energy, the heat into space. So small enclosures, and that's why a lot of these data center ideas they're talking about are actually constellations of smaller devices, of smaller vessels that communicate with each other to create a coordinated data center, probably with lasers. So over the years, various memory and storage technologies have been used in outer space. Hard disk drives have been used in some space missions and in laptops on the International Space Station. And note today that hard disk drives are being produced that are hermetically sealed and filled with helium. So they could operate in a vacuum environment, for example. They may have other things like gyroscopic effect from rotating disks that you have to take into account, but they potentially could work in space. SSDs are a more popular storage technology for outer space, as you see from some of the things I talked about. To avoid data errors, space SSDs use radiation-hardened controllers and special error correction in order to safeguard the data. DRAM faces significant challenges in space due to radiation-induced hard and soft errors, so we may need to think about something besides traditional DRAM as the memory that we use in space. And on that side, there are several non-volatile memory technologies that might be used instead of DRAM for space-based memory, including magnetic random access memory, resistive memory, ferroelectric memory, that are not sensitive to radiation. They're not storing charge like a NAND flash or DRAM is. So here's some examples of some of the things here. So Infineon acquired, they acquired Cypress Semiconductor in 2020. So they're actually here in the Valley, and with it, its memory business. So the company has a suite of non-volatile memory technologies that are targeted for near and outer space applications, and they include NOR flash devices, as well as ferroelectric random access memory devices. For example, you can find information. There's a picture of it up there, and you can also find it, on their website, I think. Everspin is a company that makes various types of MRAM technology. So it's currently being used. MRAM is being used for space and aerospace applications. The spin tunnel torque MRAM, which is the higher capacity MRAM available today, stores data using magnetic states rather than electrical charge, and that makes it resistant to that radiation-induced errors and immune to single event latch-ups. Everspin is the oldest standing MRAM enterprise. They spun out from Freescale many, many moons ago, and they say that their MRAM can replace slower and less reliable flash memory and SRAM, static random access memory, for tasks like boot code, data logging, and FPGA configurations in satellite and other space systems. MSA Components offers a space-grade non-volatile memory based upon MRAM from Everspin. There's a company called Enhance that has an FPGA with MRAM memory for space applications as well. Another company, Avalanche Technology, has been advertising their MRAM for use in aerospace applications. They have a VNX Plus regularized storage device with up to 8 gigabyte capacity for military aerospace and low Earth orbit applications. They wrote a white paper actually on using MRAM in data centers in space. You can see the picture there. It's actually a constellation of interconnected devices, but include large satellite and small satellites. And the company is designing a moon drive, they call it, for deep space applications, currently up to 1 terabyte, but it's in the 6U form factor, so it's not very small. But with their higher density MRAM, 2 gigabit and 4 gigabit devices, they think they can reduce the size of a 1 terabyte MRAM SSD. So this figure below that is a white paper outlines an array of small satellites, creates a network of high performance data center nodes. And this the network connects smaller constellation satellites and larger data center satellites with MRAM acting as the multi-image bootloader, a compression decompression buffer, and as a storage buffer, or even as the main storage, or complementing a larger storage device. In March of 2023, Kioxia America announced its participation in the Hewlett-Packard Enterprise Spaceborne Compute 2 SBC2 program. So in this program, Kioxia SSDs provided flash storage in HP Edgeline and ProLiant servers in a test environment for conducting scientific experiments aboard the International Space Station. So this is part of a greater mission to advance computing and reduce dependency on communications by providing local storage as space exploration expands. So this shows SPC2 HPE servers. Taiwan-based SSD controller and storage product company Phison announced that their SSDs had been certified to be used in lunar data centers in 2022. That's interesting since we don't have them yet. But Phison Electronics supplied the company's Piscari enterprise-grade SSDs to deliver over 1 petabyte of storage on the AX-ODC node on the International Space Station. Piscari SSDs used for space applications are modified from the general enterprise Piscari SSDs so they can work in outer space. And the D200 series modified SSDs used in that Lodestar lander could operate in extreme temperatures from -280 to 260 degrees Fahrenheit, and they're radiation hardened to withstand cosmic radiation. So they're also built to endure launch vibrations, high G-force, and working in a vacuum environment. In addition to the ISS and various lunar data center missions, Piscari SSDs are being used on the Mars Perseverance rover. Iridia, I've mentioned them before, they're making a synthetic DNA storage among a few of those startups. With Arweave, an open source protocol for permanent data storage, and the ASI Alliance on the creation of the cryptocurrency token stored on the synthetic DNA on that Dragon Aerospace Blue Ghost lander, which I showed a picture of actually on the moon earlier. So following the spacecraft's landing, the public keys for the tokens were shared on the Iridian website so people can see and potentially interact with these lunar-based assets. So they're trying to create some engagement with this. An 5D memory crystal from S-Photonics, another startup company working in archival storage, containing art and technology curated by Moon Mars Museum, was launched as part of a space renaissance for all payload on a SpaceX Falcon 9 rocket in June of 2025. It included Chabal cave paintings from France that are over 32,000 years old, actually images of them, not the actual paintings. These images were etched into the quartz structure with representational artwork on the exterior. The spacecraft is scheduled for a lunar landing sometime this year. S-Photonics said that a different SSD memory crystal is part of Elon Musk's SpaceX Falcon Heavy 2018 launch, containing a copy of Isaac Asimov Foundation trilogy and placed into the glove compartment of the Tesla Roadster launched into space at that time, if you remember the images. So let's see.
And that's still going out, isn't it?
It's still going out, yes. It hasn't caught up with Voyager yet, but
yeah.
So where do we
mean by 5D?
They call it 5D. So
Yeah, be sure to repeat the question.
yeah, the question was why they call it 5D. It's a quartz crystal, and they actually record inside the volume of the quartz crystal. Now, why that's 5D, I don't know, 5-dimensional some kind. You know? Maybe there's strings in there, you know, some little tiny strings. Yes.
The previous slide, the future.
The previous one?
The future, yeah, no.
This one.
Slide about future.
Yes, to the stars.
The future of data center in space. That slide, the future.
Did I?
Again, you have to repeat the.
Oh, he said I have a slide on the future of data centers in space. Did I missed it? You mean this one? Yes. This is the future. So radiation-hard digital storage and memory will be essential in outer space, of course, and we're going to need processing and communication technologies to support a far-flung extraterrestrial civilization. It won't be long before there are more data centers in space than on the Earth. This is my own view. And likewise, in the future, there will be more manufacturing, materials harvesting, and even human habitation in space than on the Earth, because there's more of space, there's more stuff, and there's more possibilities out there than here, I think. And this could lead to less pressure to develop Earth resources and incumbent problems with that, and help make a more sustainable world and provide new opportunities to achieve, I believe, happiness and plenty, or at least, you know, exciting and interesting things to do.
So,
yes.
You mean the future of space or future of data center in space?
Well, the future of space, but data centers will be part of that because we need our digital processing to do stuff.
So can I ask a simplistic question here?
Mm-hmm.
So if DRAM is not going to work.
Well, DRAM it's harder to get DRAM to work. Yeah.
Do we have hard DRAM with the same performance?
Probably, I imagine you're going to have to make some sacrifices to DRAM performance to get it to work.
Ask how affects the data center processing capability and speed if you only can use the flash, basically.
Well, no, they're talking about that's where these other memories come in. That like there's a spin orbit torque MRAM technology that would be faster than traditional than tunnel torque. So there's technology being developed in these new memory technologies that could eventually replace DRAM or be used in these applications because they're more radiation resistant. Yeah. Yeah. So as humanity moves beyond the Earth to use the vast energy and material resources available in our solar system and someday beyond, we're going to need processing and communication technologies that support a far-flung extraterrestrial society. And that's why we need the data centers. So, yeah. Oh, online?
A question. This gentleman right here.
I was going to ask how SRAM.
Oh, SRAM has problems too.
All right, let's repeat
Yeah.
the.
The question was how SRAM does in space. SRAM has problems too, like DRAM does. And that in particular, things like magnetic random access memory is already being replaced or supplementing SRAM in consumer devices in a lot of applications. For example, in that case, it's because it allows you to have more low power states for battery powered devices. So I think that there's alternatives to SRAM as well that people are going to be using in outer space.
Do you think Tom, data center in space scale to replace data center on terrestrial data center on Earth?
Well,
All right, have to repeat.
so the question was whether you can data centers in space could exceed
Replace it.
replace data centers on the Earth.
Yes.
Maybe, but I think you probably will have both.
Okay.
Right. I mean, wherever you're doing stuff, you got to have, nowadays we're doing everything with processing and communication. So wherever you are, we need these kind of capabilities. So, but I think that in the long run, there's going to be, again, looking at where things could be, humongous opportunities, resources, energy, more places for people to do things they've not done before. It's exciting. It's interesting. It's a frontier. I think that as the cost goes down, that will become very attractive to people. And
This is also, it won't be long before there are more data centers in space than on Earth. That's the
Yeah.
answer.
yeah, I'm saying that. I'm not saying this is 10 years from now or so, but within the lifetime of some people in this room, let's say at least.
Younger
Not
people.
necessarily all of us.
Not necessarily all of us. So
Yeah.
humans in space. So we talked a lot about, machines and stuff, but as our technology opens space to human development, we'll also live in space because we don't want the machines to have all the fun. So that's going to create demand for new types of food technologies, for instance, support humans in space and deal with radiation and other hazards, which we are also sensitive to and doesn't do good things for us. The question is, will we live in tunnels like lava tubes on the moon, or are there other more open options? And this might include terraforming Mars, which we know Elon Musk wants to do that, for example, but other possibilities as well. So there's also, this brings up new challenges, new things, which people that are interested in technology, we like challenges, and especially this opportunity and the possibility of generating wealth and other good things. So in closing, I just want to let you know that if you're interested in some of those new memories that are going to be used in outer space, I just happened to do a report on that. And I have a few of my flyers here, and you can see the links to get this. It's done by a colleague, Jim Handy, and myself. So I wanted to let you know about that. This is the giant compendium of new memory technologies. It's over 300 pages, 200 figures, 34 tables, and 175 companies profiled. Also, I want to let you know about IEEE has this thing called the Future Directions Committee, and they're supposed to be doing stuff which is looking at the future. So we've got one that's actually going to be probably approved next week officially, which is a space tech initiative. And topics that we're going to be looking into are space mining and manufacturing, space robotics and automation, long-term human habitation, debris mitigation, that's all the junk going around the Earth, space sustainability, non-terrestrial communications, and standards, of course. So there's that. And then, one more thing. So I'm a co-editor of a special issue of IEEE Computer Magazine in June of 2027 that is going to talk about computing or looking for articles on computing and communication in space. And so the call for papers is going out, and that's kind of what this is.
Is there an interest in detecting human health in space?
Well, human health in
Yeah, detecting,
Repeat the question, please.
Oh, is there any interest in
health management.
in space? Well, one thing, people talk about this. I mean, there's issues in going into space. For instance, people report bone loss, things like that. But also, it may be easier on people with heart conditions, for example, too. So maybe, because you have less of the stress of gravity on you. So it's a new environment. And we were not built for that environment. So, we'll have to create conditions that could maybe use what there's advantageous about it, but also overcome what is not.
NASA is very interested in devices which detect health problems in
Mhm.
space, because
Yeah.
once you're up there, you get cancer, you may have 3 years where you can get back, so it's a problem.
Yeah. Oh, yes, communication issue. Yeah. You have a question?
Yeah, hey, Tom.
I'm near the end, so you could question.
We didn't, so serviceability is obviously an issue in space. And, is that part of
It is right now because we don't have stuff out there to do it.
You gotta
Oh,
repeat.
the comment was serviceability is an issue in space. It is if you have to go up from the Earth to fix it.
Well, any way you look at it,
Yeah.
it's a serviceability issue.
Mhm.
So how is that being addressed?
Well, as you get more stuff up there and more equipment up there, presumably it also would you'd create an infrastructure for servicing that capability as well.
Your droid would service it, right?
Well, that's why I was talking about the physical AI, which is basically robotics. We're going to use a lot of robotics when we're not.
I mean, robotics is one way, fault tolerance systems.
Mhm. Yes, yeah. Yeah.
There's a lot that goes into servicing data centers here on Earth with people.
Yes.
doing stuff.
Yes. But a lot of data center, but it's only a handful of people in some of these really big data centers, right?
Well, they can do things like over permission.
Well, and also, they were talking about some of these NVIDIA-based data centers having like a 4-year lifespan or something like that. So if that could be both because of radiation damage or other issues, but also because it'll be outdated by that time. You'll have better stuff.
Seems very short.
It does seem short.
Like normal, I actually worked at a satellite company when I was in college.
Yeah.
They were doing reliability models on a 10-year lifespan.
Yes.
You'll have to.
Oh, the comment was that a lot of times with satellite development, one of the participants' experience is they would design for a 10-year life.
And a lot of that is because the propellant is limited, not because the thing fails after 10 years.
Oh, so a lot of that statement was that because the propellant is limited because they have to reposition themselves.
Propellant tank.
Yeah.
For changing attitude.
Right. Well, and if you're, depending on where you are, if you're in near Earth orbit, you've got this big gravitational well that you got to fight against, right? If you're further out, you may not need as much.
Even like these are geosynchronous, so
they're out of ways. Yeah, but they still have to adjust. And you still need to do that. But when you start getting the stuff from outer space versus having to launch it up from the Earth, like you mine asteroids and things like that to get resources, or comets to get water so you can make fuel and things of that sort, then it becomes, it becomes its own economic system in a sense, connected to ours, but, having its own resources, capabilities. Anyway, so here's my summary that I think lower costs for space transportation are going to enable a lot of interesting stuff, essentially the possibility of the actual humanization of outer space. And we're going to, I think, increasingly depend upon resources from space as time goes on. It's a huge frontier. There's a lot of stuff out there, energy, materials, and opportunity. And physical AI will be important. Part of that, semi-autonomous robots needed for developing and doing things in space, and in places where there would be dangerous for humans to do it, for example. And that's going to drive demand for data centers in space. I think that's the big driver, is because people are going to be doing stuff in space, and wherever you do stuff, you have to have the infrastructure to support it. And building those data centers that require new memory and storage technology is going to require other things as well, some of which we may not know about yet. And there are well-funded space data center projects currently underway, like everybody seems to be jumping on it. And I think those developments finally will help us to develop outer space as a new human frontier with new opportunities and fascinating things to learn and new ways in which people can live and work. So with that, there's my references, and I want to thank you for the chance to talk to you today and share this with you.
Oh yeah, let's do the raffle first. And then we got some questions online, and then there might be a few questions in the room. I wouldn't be surprised.
So there was a question of whether I would share the slides, and yes, I'm willing to share the slides. So, you know,
They're typically posted on the CNSV website. Can I pick?
Yeah, if you
Or
like,
Tom can pick.
mix them up a little bit and.
why don't we tell them what it is first?
Yeah.
Okay.
So this is a book by a guy. It's actually on basically an outer space economy. And so we got a copy of this thing, and I'm actually just reading through it. I haven't read through it yet, but it looks interesting. On how space-based economy could be developed, what sort of resources and even attitudes and things people have to make it possible. So with that, we are going to
I'll hold it up.
give this copy away.
Okay, and no CNSV board members are in the pot, only attendees. So this increases your chances to win.
And I believe they have to have their ticket out because there are no names on this. So get your ticket
That's
out.
right, you need your ticket, you need your number.
Okay, are you ready? How many numbers do I have to read? For the last three?
I'm not sure, at least 4, I would say, at least.
Ending in 470. Do we have ending in 470? Last 3 numbers. Oh, we have a winner.
We have a winner.
Excellent.
All right. So come right up.
And are there any other questions?
Yes, I got some. I'm gonna hit the Zoom questions first because people
please.
have patiently waited.
They have.
So, sir, what is your name?
I'm Praveen.
Well, Praveen, congratulations. You have
Thanks so
won the
much.
raffle tonight. Okay, so let me hit some of the questions that came in online. Okay, and we'll want to repeat the book title again. That was one question. So can you say it one more time right now?
What was it? The Cosmos Economy is the book by, thank you. Yes, it's Jeff Gray. Yes.
So we'll post that also because that's a key part of this presentation. Here's one of the questions online, and I'm going to paraphrase a little bit. I'm just going to stand behind Tom so I don't take the camera away, hopefully. But everybody can hear me in the next county even, so I don't think we'll have any problem there. This question is one that Tom already actually alluded to, space junk.
Yes.
What are we going to do with it? Tom suggests recycling, that kind of thing.
Mm-hmm.
But I've also often wondered about that we have so much. Is it hard to launch through all of the low Earth orbit space junk? And now we got multiple companies that want to launch these large constellations of satellites for data centers. Do we have a solution? Is recycling our solution? Is burning it up? Is nuking it? What are we going to do?
Well, nuking is probably kind of messy.
Laser nuking,
Laser.
just blasting it,
Well, if you make it in smaller pieces, there's more stuff, I think the real answer is you got to take it out of there, and you could either force it to fall into the Earth's atmosphere and burn up that way, which I personally think is kind of wasteful.
Is there a problem launching through it at this time? Is it easy enough to miss?
Well, so yes and no. It's easy until you hit something.
Yeah.
Right. I mean, for pilots, they have this idea of the big sky, right? Until you get to an airport where planes tend to be in fairly close proximity, the chances of them hitting each other are not very good, but it does happen, right? And if you spend a lot of money to put something in space, because it still is fairly expensive to do that, having it be wiped out by something that hits into space, within a month or a day from it launching, being up there, probably would be kind of a shame. So my own feeling is if you spend a lot of energy to bring it up there, keep it up there, but put it someplace where it's not in the way. Like move it to a Lagrangian point, where the Earth and the Moon's gravity balances out and things tend to stay there, until you can do something.
Pretty far out though, right?
They are pretty far out. Yeah,
quite a distance.
Yeah.
Yeah.
But I think there's an opportunity for startups in space garbage collection.
Garbage, the next frontier. Everybody, you heard it here first, so don't forget this. Could you comment on what specific techniques are used to render the storage technologies you talked about, SSD, hard drive, the memory stuff, resistant to radiation-induced bit rot and damage.
So there's things you could do in the devices, more error correction, a lot of redundancy.
Yeah.
But you're also fighting against technological issues, which ultimately can cause failure. You can shield something, put lead around it, for example, and that, or other materials which could keeps, depending on the radiation and its energy, could keep that from hitting it. But ultimately, I think you have to look at technologies that are less resistant to radiation failure as being an important component of that. So I think this is probably going to drive some of these new memory technologies to have more applications, especially in space than they have now. But also, people are finding ways of doing SSDs in space, by making the controller radiation hard, probably putting, shielding around it, and then a lot of error correction and redundancy, for example. So it's going to be a combination of things we know how to do now and new stuff.
You mentioned hard drives and having what was it, a gas in the hard drive because helium. I mean, a lot of the heads have to fly, right? They have to float against the drive surface.
That's why you need the helium.
That's why, and the helium will still serve as enough to keep a head flying.
Yeah, actually, it's pretty cool. And they originally were using the helium. Some companies were using it during the servo writing of the heads. They actually would pump helium into them during the servo writing. That's kind of how this whole thing got started. And they said, well, why don't we just keep it in there and seal this?
And seal it.
Yes. And so that led to I think it was HGST at the time, back 2013 or something, introduced the first hermetically sealed helium-filled hard disk drives. Helium is pretty cool. It actually causes less flutter because it's a lower density medium, than air would be. It also, of course, if it's hermetically sealed, then it doesn't care if it's in a vacuum or not.
Right.
So there's a lot of interesting things about that. And the other thing is the helium actually draws heat more readily than air does. So the drive runs cooler as a consequence of that. Less flutter, less friction caused by that, and it moves the heat out of the drive better.
And there's another question here: should we bring back bubble memory?
You can, yes. In fact, there's not exactly bubble memory, but does anyone remember racetrack memory? That concept, Stuart Parkin's racetrack memory, IBM.
Mm-hmm.
Okay, so there's a startup in France that actually has a vertical thing, and they're storing domain walls and a magnetic pillar as a memory device. And actually, they want to use it for somehow use it for a computing device as well. So yes, there's all kinds of interesting magnetic stuff people do.
And maybe comment on. I would think there's a weight penalty for a hard disk drive versus SSDs. Is that right or not right? Weight, and certainly there's moving parts that you don't have with SSDs.
Well, it's an interesting metric, capacity per pound, right? And I don't know.
Is it higher? Is it higher for a hard drive?
I think it may be, but I have to go look. I have to figure out, equivalent of how many, and then what capacity of NAND flash chips.
And how much energy it takes.
I don't know the answer to that. I have to look into that.
All right, so Tom Coughlin is going to get back to us with that insightful thing. Here was an important comment. Yeah, then we'll go to the room. Last comment from the room. This gentleman says Elon's Tesla Roadster is not going out in a stable solar system orbit. That is still somewhere kicking around Mars or something like that.
Oh yeah,
I thought it was heading out.
No, okay, well that's a good correction.
All right.
And he wants to go to Mars anyway, so he's going to need some way to get around once he gets there, right?
Right. Yeah, but please repeat any question from the room. So.
Well, it's one in the back first. Yes.
The reference was to far from extraterrestrial society.
Yes.
And I'm curious, what you might, or do you know anything about that?
Well, I've read a lot of science fiction stories. What?
As far as the people and who's involved in what projects.
Oh, well, I just think it's going to be a natural thing. If you start getting out there, once you're out there, and assuming you can live out there, right? Oh, the question was about creating a far-flung civilization. Yes. Yeah, I was saying that, but people being out beyond even the solar system, I think it's just a matter of time. It's kind of like diffusion. Once you're out there, and people, start, having kids and doing other stuff that people do, they're going to start spreading out and going into other places. And ultimately, we want to go and actually check out other stars. Now, is there a way of doing that fast? We don't know it yet. There's certainly a lot of science fiction stories that have warps of one sort or another that get you someplace.
They did it on Star Trek, right?
Yes, yeah,
So,
but we don't know how to practically do that yet. Oh, actually, there are some theories about that they require incredible amounts of energy to bend the space in front of your vessel, so that you, so you sort of slip through it much faster than the speed of light. There's some theories around that. You're changing space by applying energy to it. Anyway.
sounds like create your own black hole.
Yes, there's, okay. Like an ion, one of those ion drives or something like that.
Repeat.
A fusion engine. How long to get to the nearest star? It all depends on how long you're able to run it, and the speed with which you're able to get to that thing. The other thing is you're going to have to slow down too if you want to stop. So you got that part of it you have to deal with too. So it depends on the design. But people talk about being able to go out to like Proxima Centauri or things like that, and potentially, again, depending on the speed, a few tens of years, for example, possible. You had one.
When it came to like space travel, I was gonna say like the black hole conversation, like
Yes.
build a tesseract or something.
Well, white holes are. The question was on space transportation. Want to get into all the cool theory stuff? It's like if I have a rotating black hole, then you could have, one end essentially is the sucker part, and the other one is at the other end of it, that you could actually have what they call a white hole, which actually emits the stuff that was sucked into the black hole. So that's one theory, and if you could do that and survive doing that process, which is a big question, that might be one thing, but we haven't found white holes, so we don't know if they actually will do that yet. We have seen black holes, though. Yes. Okay.
Tom, to make the economics work, is there any rough forecast in 5 or 10 years how many satellites going to be deployed? Order of magnitude?
Oh, well, if you list, what Starlink was, Musk, SpaceX, they're talking about 1 million satellites.
Really?
Yeah. And I think there's tens of thousands of satellites that everybody else is talking about putting up there. So a lot.
It's a big number.
It's a big number.
For semiconductors, it's a small number.
Well, yeah, but
Figure out the economics.
You're talking about doping space? Or?
No, I'm just a billion chips to power, for space power, and I'm trying to figure out what's their business case.
Oh, you mean on the semiconductor side? Well, there will be, if this takes off. Yeah.
10,000, it's just like, the return call from the foundry, it's like 10,000 wafer starts a month, maybe.
But they last only, the idea is they last only 4 years.
Well, enough boys, and I'm trying to figure out.
Well, one of the things they're talking about is this could be a near Earth orbit factory making drugs that are hard to make on the Earth, or defect-free crystal structures, things of that sort. So, or more, or the opposite, really amorphous stuff. So there's all kinds of possibilities, things people are looking at, and you'll find out more stuff when you get out there and start playing with it. Hashem.
Yeah. And we say, Tom, that data centers in space are good for orbit, edge computing in the orbit, but will never replace hyperscaler data center.
Well, I think it's you're still going to. So they may supplement, and they may they'll supplement initially, stuff we have on Earth. Okay. Ultimately, I think because if you have people out there and all this infrastructure and doing all kinds of things, you're going to need the data centers to support it up there. So that's why I say ultimately, I think we'll have more stuff out there than here. Yeah.
here,
Oh, sorry. Oh, sorry. Sorry, Ray.
How do you see a space-based garbage collection economy developing, and how do you think it will get paid for?
Well, that's a good question. Well, first of all, it could be part of an insurance policy that if you get the stuff out of the way, you'll have better launch achievements. Especially the things that get crowded.
Rates, lower insurance rates.
Lower insurance rates. So it could be an insurance play, for example. I'm just thinking out loud, things you could do. But it could also be you're harvesting stuff people have already spent the energy to launch into space, and ultimately that could become raw materials for doing other things. So if you put it someplace where you can keep it, you know, not in the way, then that could be a, you know, resource as well. So that's another possibility for, you know, now how long it takes for that to happen, I don't know.
Like straight up Hormuz, though, I mean, you just put a toll on everything that's launched, right? And then you clean up your trash with the toll. So,
Or garbage collection services, yes. Well, there's that too. What, the garbage collection? Oh, well, he's recycling rocket components, yes. Yeah, but once something's in orbit, you know,
yeah.
it's how do you deal with that? That's the issue people are dealing with.
That principle doesn't work so well when you have a bunch of small debris, which is what we have. We have a huge number of very small pieces that are still big enough, given the speed you're going, to cause a lot of damage, and cause cascading debris like Kessler syndrome, etc.
Right.
So that's going to be the stuff that's really difficult to do. But garbage collection, or maybe like snow plow.
I mean, that little debris will penetrate
Or
a device up there.
or a net, kind of like fishing, you know.
Yeah.
But you have to match. Sorry.
Repeat that for the Zoom people.
Oh,
yeah.
let's see. What was it, the
small size debris.
Oh, small size debris is going to be hard to pick up, so you have to figure out how to do that. Yes, agreed. But there might be ways of doing that. You have to. The big thing is you have to match the velocity of stuff. You don't want to tear through whatever it is you're collecting it in. So it's kind of like you have to catch this stuff, and then change its orbit and get it out of wherever it's at.
Any other questions? And then we should probably wrap up.
We should, because
Covalent can go home. And once again, Tom, thank you so much. This is a great call.
Thank you. Thank you all for coming.